Hello everyone, this is the third presentation of the Budapest Deep Learning Meetup, and the topic is what could we do if we don't have enough data. My name is Miklós Tóth and I'm going to have multiple presentations on this topic. So in this section I'm going to build on the previous presentation done by Levente Szabatos, and in case you haven't watched that video, I will copy this link to the description below. And please watch that video before this one, because he talks about the theory part of this topic. And in this video, I'm going to present the practical part. So I'm going to present you a notebook where we go through each and every solution for this problem. And yeah, so this video doesn't contain any slides. I will sometimes switch to Levente's presentation, but in most of the time I'm going to be in this notebook. So where could you get this notebook? This notebook is at my GitHub account, so I'm going to copy this link to the description below. If you want to, if you want to download the source code and play around with the numbers a little bit, you could do that too. So let's start. So the first problem, or the first problem which was demonstrated by Levente was the imbalance dataset. And in this case, we will have a majority class and a minority class, and the problem is how to tell the algorithm that the minority class is kind of an important term for us, and where to draw a decision boundary between these two classes. So yeah, let's jump back to my notebook and let me run the first cells, and I'm going to go through the cells here. So the first cell is kind of just importing some libraries, and the second cell is kind of generating or regenerating some random values. And in this case, I kind of regenerated what Levente had here, so an imbalance data set with kind of random points here. And yeah, so in this case, we will have two x values, so two features, x1 and x2, and we will have two categories. So one category is for the majority class, which is -1, and the other one is the minority class flag, let's say, which is 1. So 1, -1, and 1, you will see that we will use support vector machine to solve this problem. And support vector machine works with these two classes. So support vector machine cannot really work with 0 and 1 classes. So let's plot this data set in this notebook, and I'm going to show you that we will have the same issue with the majority and the minority class. So if you would ask a real person to draw a straight line, a kind of decision boundary between these two classes, he or she would maybe say, okay, the data is kind of overlapping, and in order to draw a line, maybe someone would choose this line, right? Or maybe there could be another person who would say, okay, the orange class is really important, so he would draw a line here. You will see that machine learning algorithms have problems with this because there are much more blue points than the orange points, and for an algorithm, it doesn't really matter. It doesn't really matter which color is it. It will try to find some kind of balance between these two points, but since the points are overlapping, the algorithm will get kind of confused. And let me show you just another case where we don't have, let's say, an overlapped data. So let me show you, let me modify this term. Yeah. So I just modify the cluster centroids for these two. And in this case, you would say that that's an easy task, and it is. So an algorithm would draw a line somewhere here, a decision boundary, and then we don't make any error in that case. But the point is that we have overlapping classes. So we will check out, okay, what's the algorithm says in this case. And just to make sure how imbalanced our data is, I will plot another diagram which shows that, okay, the category 1 class has kind of like 1000 samples, and the minority class, which is category 2, has something like 150 samples. Okay, and so we are going to solve this problem with the support vector machine algorithm, and yeah, with TensorFlow. So let's first split the data into training set and evaluation set, and then we will introduce some variables in TensorFlow. So I'm going to run this cell too, and now we are going to implement the hinge loss. So what is this hinge loss? This hinge loss is commonly used for supervector machines, and it works like you will count together all the errors for each and every samples. So we have like let's say 1150 samples minus the evaluation set, so we will have some kind of like 800 different samples, and this loss function contains kind of a, let's say, prediction. So we could call this a prediction, a P, which will all the time try to predict, okay, what kind of value is it. And during the training, this W term and the bias term will be trained and modified in order to have this P value all the time the same value as the Y value. So let me just show you some examples about this. So let's assume we have Y1, YI values and these prediction values, and then I'm going to show you that this L is, I'm going to show you what kind of value L has. So let's say our algorithm works really perfectly. So if there's a Y value with the majority class flag, which is -1, and our prediction will be also around -1. In that case, -1, so -1 by -1 is 1, and 1 minus 1 is 0. So in that case, this term will be 0. So the loss will be somewhere around 0. Okay, there's a regularization term here, which we can skip now. And what if our prediction not really working? Then in that case, maybe Y value could be -1 again, but the prediction would say, okay, that is maybe another class, and it will predict 1. And in that case, you will see that -1 by 1 is -1, and 1 minus -1 is kind of 2. So in this case, we have generated some error. So our loss in that case will be somewhere around 2. And you know, during training, the training will all the time modify this W and bias term in order to minimize this loss. So this is how the hinge loss works. Okay, so you don't have to read this line by line, but please accept that this part of the so this cell will actually just implement this loss function with TensorFlow. So you could find all the terms like subtract term and also matrix multiplication, which is this part. So you don't have to read it now. Later you can also go through this. The point is here that we have generated a function for this hinge loss support vector machine function, algorithm. So in the next step, we are going to train this with TensorFlow, and I prepared a training function in order to use this many times. So in this presentation and in this notebook, we are going to modify the loss function. Therefore, we will use this train function more than once. So this train function accepts a loss candidate, which in this case will be the normal hinge loss, and some training data and some weights, but please now just kind of ignore these weights. We won't use these weights for the first run. So in this train function, we are going to use this gradient descent optimizer, which is kind of the commonly used optimizer, and we are going to run 10,000 epochs. Why 10,000 epochs? Since we have not so much data, we are going to be able to run this within seconds. And yeah, please ignore the weights. So our training function and feeding the data into this loss function is here. And yeah, we are going to run this like 10,000 times. Okay, one more addition to that. Our training function also does the prediction after the training. This is good because we can then easily check, we will be able to easily check, okay, what are the error terms and what are the F-score, recall, and precision scores for this model. And we are going to also find the final slope for this model and also the intercept. But let's talk about these terms later. So let me run this cell, and in the last line you will see that this function is called with this normal hinge loss. And as you can see, the algorithm started to train on this data set, and yeah, it's already finished. So as you can see, the loss in the beginning was kind of a huge value. The reason is that there are some random initialization, but after some epochs, actually the loss goes down and down to 0.2. So there are not too many errors generated by this loss function. And during the algorithm, this slope and intercept is also calculated, which helps us to draw the decision boundary for this algorithm. So let me plot this model first, and then we will run a kind of report on this. So I have created some functions which can plot the decision boundary for this model, and yeah, you will see that the decision boundary is, yeah, let's say maybe suboptimal. So what do I mean by this? So this decision boundary says everything on this side should be the minority class, the orange one, and everything on the other side should be the blue class, the blue one. And as you can see, this algorithm sacrifices a lot of orange points to be on the blue side. And give yourself some seconds to think about this. Why is it like that? So the reason for this is that the data is imbalanced. So, you know, this data is really overlapped, and the problem is that, let's say, behind these or among these orange dots, there are a lot of blue points. And since for the algorithm there are no weights, so it means one orange class or making an error on in an orange class is the same for making an error in the blue class. Therefore, you know, it kind of sacrificed some orange points and said, okay, let's draw a decision boundary here somewhere. And the question is, okay, how to solve this, or what are the solutions for this in this with this support vector machine function? And one solution, which also Levente showed, that we could modify our objective. So with other words, we can modify the loss function, and we can make the algorithm to make more serious issue by predicting on the minority class, which means making an error on the minority class should be more penalized. And it turns out that this can be easily done by modifying the loss function. So let's introduce the weights, some weights for this loss function. So what do I mean by weights? So in this cell, I'm going to kind of penalize, or let's have a kind of multiplication number 2.5 for penalizing errors on the minority class. And I'm going to take this number and kind of inject it in this algorithm. And in that case, what I'm going to do, if the y1 is the minority class, which is 1, I'm going to multiply this term by 2.5. And with this move, actually I penalized the errors on the minority class. And if there's a majority class, there's no penalization. So in that case, the multiplication value will be just 1. Okay, so by this, kind of forcing the algorithm to make less error on the minority class. So let me show you how this works. So this is the modification of the loss function. And then I'm going to call this train function. So let's run this, and let's run the train function. And let's wait until it trains. Good. Okay, it finished. So as a result, we got some other slopes and intercepts, and let's plot this. So let's show the decision boundary. And yeah, so as you can see, the decision boundary just moved a little bit from here to somewhere here. And the reason for this, that making an error on the orange class generates higher error, therefore the algorithm will move the decision boundary. And let's compare the values, or let's compare some metrics on these two. So let me just go back to the original one where we had this decision boundary. It's kind of, yeah, maybe suboptimal way. And let's print a classification report on this. So in this case, you will see that, okay, this is the previous case, so let me retrain this just quickly, because I'm using the same variables. So just a sec, and it will finish. So running a classification error report will show us that in the previous case, in the first case, the category 1 is the majority class and the category 2 is the minority class. And you can see for the major class, the precision is kind of good, the recall is really good, it's almost 1, and therefore the F-score is kind of 0.94, which is really good. But for the category 2, as you can see, the recall is kind of not really acceptable. Therefore, also F-score is also not acceptable. So recall 0.1 means, in case you're not familiar with this, that it will, so if there's an orange point, it will find it only in 11% of the cases. Yeah, which is really bad. Good. Okay, so let me show you how it's changed with this loss function, or with this trick penalizing on the minority class. And I'm going to print a classification report on this new one. And you will see that we got much better values, and these values are kind of acceptable. Yeah, let's say it's much better. So for the majority class, the category 1, the precision got a little bit better, but recall got worse. So this is kind of sacrificing some majority class points. But the good one, that the F-score is still good. And look at this this one now. For the category 2, you can see that the recall got much better, and the F-score is kind of acceptable. So this means that actually we could trick this algorithm and had a better decision boundary on this whole thing. So I'm going to stop the video now, and I'm going to record the next solution, the undersampling solution, in the next video. So thanks for watching.